right, so as you can see, that 256 is a 2 to a power here. All right, so all 2's. What is my index?
5.
My index is 5. So I am going to say 1, 2, 3, 4, 5 2's. This group of 2's, 1, 2, 3, 4, 5 2's right there, that can come out of my radical as a 2. All right? So I'm going to take that out as a 2. So on the outside of my radical, I'm going to have this guy. I have these 1, 2, 3. That is not 5. So it's not 5 2's, right? And so none of those can come out. It has to come out as a whole group of 5, okay? So those are all going to stay in individually. By that I mean you have to say 2 times 2 times 2 is going to stay in, okay? So an 8 is going to stay in. Now let's look at the variable, this x cubed. Remember, we can do our division method with this. 3 divided by 5 is 0 with a remainder of 3. This tells you what comes out. This tells you how many stay in. How many x's come out? None. So all of them stay in. Anytime your exponent is smaller than your index, all of them are going to stay in because there's not enough of them to come out. All right? So that is your answer. 2/5 root of 8x cubed. Anytime your exponent on the variable is smaller than the index, they all have to stay in because there aren't 5 x's to come out. If that was x to the 7th, then I would have 5 that could come out as a group of 1, an x, and 2 would stay in. But I don't have enough, so they all stay in. All right, I'm going to be completely honest. When I do multiplication, I do not bother to multiply and see what it is because I'm just going to factor again. So I just take, first of all, this is a negative. Keep that in mind. All right. But I just take the 4 and the 16 and I start that as the base of my factor tree. Because whatever I would multiply, technically that's 64. But if I wrote 64, eventually I'm going to get 4 and 16 there. So why bother multiplying? Just start with the 2 numbers. And then do your factor tree from there. Just pay attention because you don't want to lose things in the factor tree. By that, I mean you don't want to lose that 2 being there. Okay. So that's the number that's going to be on the inside. Those are my prime numbers. And then for my variables, I have n to the 3rd and n to the 1st power, so I have n to the 4th. Okay? So far, so good? All right, what's my index on this guy? 3. So I need things that group 3's. So I have 3 2's here. I already have a 5 and a 1, so we're just going to say a 5. These 3 2's can come out, and actually these 3 2's can come out, right?
You can group them across.
Yeah, because you are multiplying 4 and 16, which is 64. So 4 and 16 are my first factors of my factor tree. I just don't bother multiplying them. 4 and 16 isn't hard. But if I had some crazy big number, why would I multiply just to go back down, right? So just start with those 2 numbers and do the factor trees, and all of those represent the prime factors of the number it would have been. So 5, 2, and 2. This is a negative of a cubed root. So I have a negative there as well that comes out of it. Because technically a -1 can always come out of a cubed root or any, index that is odd. Okay? So throw that negative out there as well. Let's look at my variable. So I actually have no numbers that stay on the inside. You see that? All my numbers came out. Okay? Into the 4th, well, as an index of 3, so 4 divided by 3 is 1 with a remainder of 1. That means I'm going to have one of my variables that comes out, and I am going to have one of my variables that stays in. Make sure you put this little index there. And then just multiply. Everything that comes out multiplies together. Everything that would stay in would multiply together. So we have -5 times 2 times 2 is -20 n. And then we have the cubed root of n. So when you have something like this, remember you can reduce on the outside. So like number 15. 5 over 4. If that was reducible, let's say 2 over 4, you could reduce the outside numbers. On 15, the inside numbers are 4 and 16. Even if they weren't perfect roots, you can reduce 4 and 16 on the inside. So any numbers on the outside you can reduce, just like you would reduce a fraction, and any numbers on the inside you can reduce, just like you could reduce a fraction, okay? Also, if you have a perfect root, do not overthink it. Do not rationalize this root. Why would I not rationalize square root of 9? Why would I not multiply top and bottom by the square root of 9? Because the square root of 9 has a perfect root. Just take it, okay? So for this one, I am not going to rationalize anything. I'm going to take the root of 9. I'm going to leave the numerator alone. The square root of 9 is 3. I am done with this problem. Do not overthink it, okay? You're done with that problem. That problem is done.
So that's why you leave the 3 is because you're gonna...
Right, it's the square root of 9. It has a root. Now, let's say, however, I had a problem like this because it did not generate one for you, so I'm going to just create one, okay? Let's say we had something like this. Nothing has a square root and nothing can reduce here, okay? So to simplify it, I have to rationalize the denominator. So to simplify this guy, I have to do square root of 5 here, which is going to be 2 square root of 10 over 5, okay? And now I'm done. I cannot reduce the 10 and the 5. Why not? One's inside and one is outside, okay? One is inside, one is outside. And so that's a problem. Now, let's say, however, that I had something like, let's say we had 5 square root of 3 over the square root of 10, all right? Let's say I have this. Nothing can reduce here either, and 10 doesn't have a root. So what do I need to do the denominator? I need to rationalize it, right? I need to do this. So I have 5 square root of 30 over 10. What can I do? The 5 and the 10 can be reduced. So I can reduce here. They're both outside. I end up with square root of 30 over 2. Square root of 30 doesn't have anything that can come out. 2, 3, and 5, right? That is as simple as it can be. 2 is in the denominator. It is not a radical. We're done with that one. So these are 3 different scenarios. You have a scenario where all I have to do is really take a root and I'm done. Or I have to rationalize, but I can't reduce. Or you could rationalize and then be able to reduce, okay? Now, keep in mind, if you can reduce up front, reduce up front. So if I had 5 square root of 3 over 10 square root of 6, I would be reducing before I did anything here, okay? So for this one, I would say, well, the 5 and the 10 can reduce. The 3 and the 6 can reduce. And I end up with square root of 1, well, that's just 1 over 2 square root of 2. Well, now I need to rationalize, right? And I can rationalize this guy as well. I end up with square root of 2 over 4. So there are different scenarios where you can reduce first. Maybe you can just simplify a root. Maybe you're going to have to rationalize. Always look for, can I reduce? But do not reduce incorrectly. I see it every year, people reducing in and out. You cannot do that. They both have to be out or they both have to be in to reduce. If you're given something like this, you're not just going to assume that you can't do anything. They are not in simplest form yet. You need to simplify them and then decide if you can do anything. So I am going to factor both of these individually. And then I am going to see if I can possibly add at that point. I'm going to do it just like I did on the first page. My index is 2. So anything that's grouped by 2's can come out. 2, this is going to be square root of 3. Plus the 3's can come out. 3, square root of 3. Now I have like radicals. What do I do? It's just like having 2x and 3x. What's it going to be? 5. So I have 5 square root of 3's, right? I do want to say if they had coefficients already, just multiply anything that comes out by what's already outside. All right, so if they had coefficients, whatever comes out is multiplied by the coefficient. Okay. So when I have something like this, I am simply going to FOIL. You just have to remember your rules of multiplying radicals, okay? All of the index on these are the same, so we're not going to have any issues. Multiply the outsides, multiply the insides. So I'm going to do this group, 5 square root of 3 times the square root of 3. All right? 5 times, what's the square root of 3 square root of 3? 3, so that's going to end up being 15, right? And then I have 5 square root of 3 square root of 3. Same thing again, right? Then I multiply these guys. 2 square root of 2 times square root of 3. The 2 doesn't have anything to multiply by, but the 2 and 3 can multiply, so I have square root of 6. This same group times that square root of 3 again, 2 square root of 6. Combine my like terms, 15 and 15 give me 30. 2 square root of 6, 2 square root of 6 gives me 4 square root of 6. That is my answer. So the whole point of division is really to simplify as much as possible. So again, you don't want a radical in the denominator, but when you have a binomial, the only way to do that is to rationalize using a conjugate. So conjugate means I have to just flip the sign of the second guy. So I am going to multiply 3 minus 2 square root of 3 on the bottom. Because I did it on the bottom, I also have to do it on the top. This guy does not turn out pretty, just FYI. Just so you know. The denominator does, the numerator does not. All right, so we're just going to FOIL here just like we did in the section above it. So square root of 2 times 3 is just 3 square root of 2. Square root of 2 times negative 2 square root of 3 is negative 2 square root of 6. Negative 3 times 3 is negative 9. And then negative 3 times negative 2 square root of 3 is positive 6 square root of 3. All right, on the bottom, I have conjugates. So I really don't have to do a lot of work here. Square this guy, that's 9, minus squaring this guy. Okay, biggest mistake in squaring this is people don't square the outside guy. It's going to be 4. And what happens when I square the square root of 3? It's just 3. So you have 4 times 3, okay? Square the outside as well. That 2 must be squared. In the numerator, there are no like terms. That is your numerator. He's hideous, but he's your numerator, okay? So in the numerator, you end up with 3 square root of 2 minus 2 square root of 6 minus 9 plus 6 square root of 3. In the denominator, 9 minus 12 is negative 3, okay? If you look at your answer key, they have taken a negative 1 out of everything, all right? So on your answer key, they did not leave the negative in the denominator. They pulled it out. So every single sign is different. It is the same answer. So whether it looks like this, which is what we get when we just do it straight up, they took a negative out, so theirs looks like this. Negative square root of 2, positive 9, negative 6, and a positive 3. That's the same answer. They just divided everything by negative 1. So remember, you want to write this as a fractional exponent. So I'm going to say 36x squared. What is 1.5 as a fraction? 3 halves. All right, there we go. That's prettier. I mean, than the 1.5. So for this guy, I am going to, well, if it'll let me change my color. There we go. Everything inside has to be to the power. So 36 to the 3 halves and x squared to the 3 halves. All right. Remember, you can rewrite it as a radical, and it may make more sense to you. So if I were to rewrite this guy as a radical, remember this is my index, so that's the square root of 36 raised to the 3rd power. That's actually easier to think about, right? And then here, I multiply my exponents. 2 times 3 halves. That's just 3. So this becomes x cubed. Right? Everybody see that? Okay.
The square of 36 cubed is just
6 cubed, which is 216. So I can now take the square root of 36, which is 6, and I can raise it to the 3rd power. 6 to the 3rd power is 216, and I have my x cubed. So you'll notice all the other ones have fractional exponents. You're going to do that with all of them. Every single piece to the fractional exponent. If it is a number, rewrite it as a radical so that you can get your brain around what you need to do first if you need to do it that way. These are really the easiest ones, honestly. These are the ones you want, okay? The reason is you're going to square both sides. Well, with these, when you square both sides, you really just have this really simple equation because the radicals go away. I have 2v plus 1 equals v plus 4. Give me that all day long, right? Subtract the v over, subtract the 1 over, I'm done, okay? And then you can plug it back in, 6 plus 1, and then 3 plus 4, square root of 7 equals square root of 7. Well, you can see that it's correct, all right? These are easy. So when you have two radicals on either side, just, solve the inside. They're going to be gone. So first you can have very simple. It equals a number. You're just going to square both sides and solve. It equals a radical. Square both sides and solve. In this case, it equals a variable. And so when I square both sides here, I now have a variable squared, which is fine. All right. I have negative 70 plus 17x equals x squared. Right? By the way, if that x squared had a coefficient like a 2, it would be 4x squared. You must square your numbers as well, okay? I'm just saying that because that was a homework question and you have to square that number if there was a coefficient. Now, when I have something like this, I am going to move everything to one side and solve, probably by factoring on these. All of these should be able to solve by factoring because I'm going to make sure they can. But if it's a difficult factoring, you can still use quadratic formula to solve for x, okay? So when I factor, I make sure my leading coefficient is positive, meaning I would not move that x squared, I would move everything else. So I would actually move the 17x and this negative 70 over. So I'm going to have x squared minus 17x plus 70. All right, I'm going to have that. So factors of 70 that add up to 17, that's pretty straightforward, right? 7 and 10, hopefully. All right. And then this is the one that you are going to want to check. You have a variable on, like personally, you might want to check all of them. But the ones with a variable on the outside are the ones that could have extraneous solutions, okay? So you will want to make sure that these actually work. You'll want to say, okay, negative 70 plus 17 times 7 equals 7. And then we have, this is going to equal the square root of, yes, that's going to work. That is true, right? And then we have negative 70 plus 17 times 10 equals 10. This is going to be the square root of 100 equals 10. Yes, okay? Now here's the deal. The biggest mistake I see on these quizzes and tests is when you plug it in and you get that and you tell me that's true. This is order of operations. It is primary root. There is no x involved. When you plug it back in, it is all numbers. This is not true in order of operations, all numbers. It is only true if I said x squared equals 49. Then x could be positive or negative 7, okay? Does that make sense? So the biggest problem I see is if you got a negative 7 here and you plugged it back in, it was like square root of 49 equals negative 7. Oh yeah, that's true. And that's incorrect. That would be an extraneous solution, okay? Does that make sense? So if I say, oh, x squared equals 49, then yes, positive and negative 7 you need to consider because it is a variable. When I just say, what is the square root of 49, I am talking about primary root and it is only positive 7. It's all numbers, there's no variable involved, okay? So when you are checking these and you plug it back in, it has to be the primary root that makes it true. And I only say that because very often you will get two answers and you'll think they both work, and the truth is one is not a primary root. And you're just thinking, oh, because it's positive or negative 7, it's true. And that's not the case, okay? So I'm only pointing that out because that didn't happen here, but it happens often in these problems, okay? Make sense? All right, let's look at the one here. This is the most difficult of them. Not that it's all that difficult, but you have a binomial here. They actually get more difficult than this, but I didn't give you one. So you're welcome. But you have a binomial. All right. So for this one, you're going to square both sides. It's going to end up very much like the other guy. You're going to have just this on this side, but you have to FOIL him, okay? Do not just square the first and the last. So this is going to be x squared minus 2x plus 1. All right? FOIL it. It is the group squared, okay? The group squared. And you're still going to move everything over. So you're still going to have x squared minus, 7x plus 12? Yep. And you're still going to want to plug it back in and check them. And in this case, they both work, actually. So x equals 4 and 3. When you plug them back in, you get 20 minus 11. That's 9. Square root of 9 equals 4 minus 1, which is 3. Square root of 9 is 3. Yes. Plug in a 3, you get 15 minus 11 is the square root of 4. 3 minus 1 is 2. The square root of 4 is 2. Yes. So these both work. Both of these are your answers. All right. Questions? All right.